Just another minute or so, I guess. Okay, so welcome everyone to this afternoon session, evening for those of us that are here in Europe. So the first talk of this session will be Grant Remmen, who's going to speak about, as we can see, causality, unitarity, and the weak gravity conjecture. So yes, Grant, please go ahead.
Thanks, Chris, for the introduction, and thanks to the organizers for putting together a really interesting conference. It's cool to be combining EFT bounds with the double copy. So today I'm going to be talking about this recent paper that I wrote with Nima, Yutin, and Jinyu Liu on tying together causality, unitarity, and what it can tell us about the weak gravity conjecture and the fate of charged black holes. So just a few words of introduction. The weak gravity conjecture, as we all know, is an ultraviolet consistency condition for quantum gravity. And there are several versions of the WGC out there, but I'm going to be talking about the classic version today, which is just the statement that for any long-range force coupled consistently with quantum gravity, there has to exist in the spectrum of the theory some state with charge-to-mass ratio bigger than 1 in Planck units. So for such a state, you can claim that gravity is the weakest force because 2 copies of that state will electrostatically repel more than they'll gravitationally attract. Now, traditionally, the WGC states are often imagined to be some light particles in QFT, but they don't have to be. And in this talk, I'll be instead considering quantum-corrected black holes as the weak gravity states. So black holes sort of solving their own problems. So what we'll be working with is the effective field theory of Einstein and Maxwell. So we have the Einstein-Maxwell action corrected by some higher dimension operators. And what these will do is they'll deform the black hole solutions, Reissner-Nordström, or more generally Kerr-Newman, or even dilatonic black hole solutions that we'll be talking about. And these modified solutions will have a modification of the maximum charge-to-mass ratio, a modification of the usual extremality bound. And that's what we want to investigate. So if I plot in the space of charge-to-mass ratio versus mass, so here I have a QFT where I might have some light charged particles, maybe not. I have the Planck scale here where everything is UV completed. And in this talk, I'll be working in the white region here where classical GR or an EFT of GR will apply. So the states of interest are black holes. And depending on the signs of the Wilson coefficients of the various operators in delta L, the extremal curve of black holes gets deformed away from the line at 1 to this red line, which I'll argue goes above 1 in various regions. And in particular, we'll be talking about 2 different regimes in this talk. The threshold regime, where the corrections come predominantly from integrating out massive states, and the asymptotic IR, where the black holes are exponentially large, and instead the Wilson coefficients are dominated by beta function running rather than anything that's going on in the UV. So just as a preview of what the ultimate results will be, as I said, we're going to be talking about this yellow asymptotic IR regime and the threshold regime. So here, m star will be the scale of the UV completion. So when I say that the black holes are exponentially large in the asymptotic IR, I mean that m star times the horizon radius is exponential in some power of the Planck scale over m star. And the threshold regime is in between that and the UV. And what we find for the beta function story is that for almost all theories, including Einstein-Maxwell, Einstein-Maxwell plus an arbitrary number of minimally coupled massless fields, n equals 1 supergravity with higher dimension operators, multi-U1 theories, dilatonic gravity, axionic couplings to Einstein-Maxwell, and even adding a fermion with a dipole operator, a massless fermion, the beta function for f to the fourth pushes q over m up in the asymptotic IR. So this red curve is below the black line in this m versus q plot. And what that means is that the infinite tower of exactly stable extremal black holes in the undeformed theory gets truncated to a finite number of exactly stable states. So in that sense, the weak gravity conjecture is satisfied. There are going to be exactly 2 exceptional theories that have various weird properties that we'll talk about, where these beta functions go the wrong direction for the weak gravity conjecture. And so looking at the details of those will be interesting. Meanwhile, in the threshold regime, we'll find that the weak gravity conjecture, unitarity and causality, and the action are all deeply related. So what I'll do is I'll review a remarkable relationship between the shift in the charge to mass ratio and the on-shell Lagrangian. Here, by the on-shell Lagrangian, I mean you just take delta L and literally plug in the unmodified extremal black hole solution, and that gives you the shift in charge to mass ratio. This was shown previously in this paper I wrote with Cliff Chung and Junyu Liu to apply for Rice-New-Nordstrom and in fact even Kerr-Newman. But in this talk we'll find it also holds for GHS black holes, dilatonic black holes, and we'll even check it for 8 derivative terms, so beyond just the leading 4 derivative operators. I'll then combine that with some statements that can be proven using the generalized optical theorem to show that for theories where the EFT begins at quartic order in the fields, the action can be written as a sum of perfect squares on shell, and so that indeed the shift in q over m is positive. All right, so that's the overview. Let's jump into it. So first, I'll tell you the story about the beta functions and bubble cuts. So we're going to work throughout this talk in 4 dimensions, and 4 dimensions is interesting for 2 reasons. Number 1, it's phenomenologically relevant to our universe, but number 2, it's uniquely in 4 dimensions that you can get this competition between the running from the leading one loop beta functions and the leading higher dimension operators. That is, in dimensions higher than 4, you don't get running of f to the fourth at one loop. So what I'm going to do is I'm going to use field redefinition and dropping the Gauss-Bonnet total derivative to write the leading order action as just 3 different operators, the 2 different f to the fourth terms and the infamous Riemann f squared term. And all of these coefficients you should imagine as containing 2 parts corresponding to the 2 different regimes we'll be dealing with. One is the term that comes from integrating out stuff in the UV, so like the Euler-Heisenberg action. And the other comes from the terms associated with 1 over epsilon divergences in dim reg, so these are the log running from the beta functions. Now, you can show via a helicity argument that I won't have time to go through today, but you can show that the Riemann f squared term doesn't survive in the deep IR. That is, it doesn't run at one loop. So all the entire game and in the asymptotic IR is in what's going on with the f to the fourth beta functions. And in fact, it's not just any old f to the fourth. If you have no dilatonic coupling, you can again show via a helicity argument that the all plus amplitude has to vanish, and so the only combination that you get in the asymptotic IR is the unique combination of the 2 f to the fourth operators that has no all plus amplitude, and that happens to be the TT combination, the total contraction of the square of the stress tensor. So it's this operator that we will care about here at first. And so we want to compute what's the beta function of A. And for Rice-Nordstrom black holes, the sign of A just directly dictates the sign of the shift in charge to mass ratio. You can read it off from the structure of the deformed black holes, and if A is positive, then we get the weak gravity conjecture. All right, so just a few words about how we're going to compute these beta functions. So the leading divergences you can show come from bubble diagrams in 4 dimensions. And so we can compute these cuts. And so this A term will be dictated by the sign of the cuts of these bubbles in the ST and U channels. And we're going to use on-shell methods to compute these. We go through how all that works in the appendix of the paper. I won't have time to go through that today, but you can look there if you're interested. And so this is what we want to compute, and we'll do that for a bunch of different theories. So first, for pure Einstein-Maxwell. Importantly, none of the terms on their own are local. You get, for example, s cubed over u cubed. But when you add them all up, you get something nice and local. You get a well-defined beta function. And here, these blobs are, in fact, just the tree-level diagrams in minimally coupled Einstein-Maxwell theory. And what you get is this famous 137 in the beta function. And we indeed find the beta function is positive. So in the deep IR, the f to the fourth terms are positive, regardless of what's going on in the UV. So we get the weak gravity conjecture in minimal Einstein-Maxwell. Great. What about adding extra matter? Well, we can do that. So this is massless matter that'll give additional one loop running. And so if you add additional minimally coupled matter, either spin 0, spin 1/2, or spin 1, it all contributes positively to this beta function. So again, Einstein-Maxwell plus arbitrary minimally coupled matter will generate black holes whose quantum corrections have Q over M bigger than 1 at sufficiently large sizes. Okay, so now let's get into somewhat more exotic theories and see if we can break this. So we've considered massless fields with spin less than or equal to 1, but what about spin 3/2? So that leads us to consider supergravity theories. So in n equals 1 Einstein-Maxwell supergravity, the f to the fourth divergence gets additional contributions from the gravitino and photino. You can compute all those. And the gravitino and photino contribute net negatively to the beta function, but regardless, the sum is still positive. But the fact that the gravitino and photino give a net negative contribution suggests maybe we should look at what happens when we add more SUSY partners, which will lead us to thinking about extended supergravity. But for now, let's finish exploring n equals 1, because we've just looked at minimal couplings. What if we add some non-minimal couplings, like a dimension 5 operator that we can build using a chiral superfield? So what this will contain is operators that look like dilatonic couplings or operators that look like dipole couplings to the fermions. So with n such chiral multiplets, again, the beta function still has the right sign to give Q over M bigger than 1 in the asymptotic IR. So for arbitrary n equals 1 supergravity, we again always satisfy the weak gravity conjecture with big black holes. No light-charged matter is needed. Now, in extended supergravity, the 4 graviphoton operator doesn't run, famously. And we can see what happens. The various different contributions for arbitrary numbers of Maxwell multiplets and hypermultiplets all cancel in pairs from different loop diagrams. But we know that the Maxwell and the hyper all have states with spin less than 3/2. And we also know that if such states were minimally coupled from what I wrote down previously, they'd contribute positively. So the fact that we're getting negative contributions here means that there must be non-minimal couplings. And indeed, there are such non-minimal couplings. There are these dilaton-like or dipole-like couplings. And I could just forget about SUSY and add these outside of a SUSY context and see what happens. So let's do that. We're trying to break this to see can we get anything that gives us the wrong beta function, or wrong sign beta function for the WGC. So let's consider Einstein-Maxwell with a bunch of different photons and add a bunch of scalars that couple like a dilaton. So here G, I, J, K are some arbitrary couplings that go like 1 over some mass scale. And I'm just going to work in Planck units for now. So G, if G is order 1, that means G is order 1 over m Planck. So I can consider a Reissner-Nordström black hole charged under photon number 1. In that case, F1 squared will go like p squared minus q squared. So if GI11 is non-zero, that would mean a generic black hole would source that scalar, dragging us away from the Reissner-Nordström solution, which I don't want. I want to still consider Reissner-Nordström. So I can take a dionic black hole where p equals q. In that case, the black hole extremality bound is modified by the term FF dual squared. And so we get that the shifting Q over M goes like this A2 parameter, where we can compute the beta function of A2. And it's a lot messier, but indeed it can still be arranged into something that's a sum of perfect squares. So it's still positive, we still get the WGC. What if this coupling vanishes? If we tune things so that coupling vanishes, then the usual electric or magnetic Reissner-Nordstrom black hole becomes an option. Furthermore, since FF dual vanishes, I can also couple in a massless axion without spoiling the Reissner-Nordstrom solution. And we compute the 4-photon divergence and compute the beta function now for these f to the fourth operators. And we get something that's no longer strictly positive. So here I'm adding in n different dilitons and axions. And I find that this achieves a minimum when this coupling is order 1 in Planck units. In fact, when it's precisely its supergravity value. And the beta functions go like 140 minus 3n. So when n is bigger than 46, that is when we have more than 46 massless scalars with these non-minimal Planck scale couplings, we can get a negative coefficient for f to the fourth in the asymptotic IR. That's sort of shocking in a way. And it's odd that we were forced to consider a kind of strange theory like this with a large number of light scalars. The same sort of thing happens with the other kind of non-minimal coupling that we were looking at in supergravity, namely the dipole-like coupling. So if I have a dimension 5 dipole here with some massless fermions, psi, if I have n such fermions, we can again get a reversal of the sign of the beta function, provided that we have greater than 137 species of those fermions, and provided that that dipole is of order the Planck scale. So you can see here in n versus g space, if you're in this relatively narrow regime of order 1 in Planck units, and n quite large, the minimum is 137 here, but generically it's much, much higher, you can get the opposite sign beta function. So what's going on with these theories? Should we be worried about that? Well, famously, f to the fourth was supposed to lead to superluminality. Namely, we have some logarithmic divided by m Planck to the fourth times f to the fourth term in the action, where here m star is the UV completion scale. So this will lead to a time advance if you have some bubble with field strength B and size L, and you're sending some perturbations through it. But of course, the bubble has a mass, and these are unavoidably gravitational theories. So there's unavoidably a gravitational time delay, which you can also compute. And you have to require that the signal that you're sending fits inside the bubble. So the energy scale that you're probing has to be bigger than 1 over the size of the bubble. So requiring that the time delay is less than the time advance implies this relationship on the size of the bubble. And it's impossible to satisfy this while remaining within the effective field theory. So what this tells us is that despite the fact that we can have Planck suppressed but negative f to the fourth operators in these theories, the superluminal time advance can never triumph over the gravitational time delay while remaining within a consistent EFT. So that's a relief in that sense. But what about the weak gravity conjecture? Can we actually RG flow far enough into the IR in these theories to find extremal black holes with Q over m less than 1? This will require black holes with exponentially large mass. So here, remember, all of my A parameters contain a UV part and some log part. And this UV part, I'll argue, will generically go like a positive number divided by m star squared. And here, this negative part we know goes like minus 1 over m Planck squared. So negative net externality indeed requires that RH times m star is exponentially large in m Planck over m star. And this immediately poses a problem for tuning, because all these weird theories broke supersymmetry. So we would expect a non-zero CC, which I can write model independently in terms of a Hubble parameter h. And to require the black hole be inside the Hubble radius, I require RH times h is less than 1, which implies extreme tuning of the CC, implies h is less than m star times e to the minus m Planck squared over m star squared. Now, we might all be somewhat blasé about extremely fine-tuned CCs. After all, our universe has a CC that in these units is fine-tuned at the level of 10 to the minus 60. But that pales in comparison to the extreme fine-tuning you need to actually realize one of these sick black holes in these theories. Taking m star pretty much as large as you reasonably could around the gut scale, just a couple orders of magnitude below the Planck scale, you would still need over 4,000 orders of magnitude of tuning of your CC to find such a sick black hole that fits inside your universe. So to engineer a black hole in tension with the spirit of the weak gravity conjecture, one has to select from three different unpalatable options. One could assume that the threshold corrections are negative, which is unlikely, as I'll explain later in this talk. Two, one could posit that there's a desert scenario just with no new degrees of freedom coupling to the photon below the Planck scale. Or three, one could posit this sort of unreasonable fine-tuning of the CC. And so this triply unsatisfactory choice implies, we think, that these sort of wrong sign beta function models are actually in the swampland. And so that's an interesting direction for future work to actually prove that. But now let's set aside the beta function story and actually look at the threshold regime. And so before I jump into why we think the threshold corrections are positive, let me review this nice relationship between the black hole extremality, entropy, and the on-shell action. So as I said, I proved this with Cliff Chung and Junyu Liu in this paper, and we reviewed it in the recent paper with Nima and Newton. And it's since actually been generalized outside of a black hole context by Gun and Penko. So here nu is a spin parameter. So nu equals 0 will correspond to extremal Reissner-Nordstrom black holes. Nu equals 1 corresponds to extremal Kerr black holes that are uncharged. And zeta is an extremality parameter. So zeta equals 1 is extremal for any Kerr-Newman black hole. And what you can show using black hole thermodynamics is that this shift in zeta goes like the shift in entropy. And it can be evaluated by just taking the on-shell action. So taking delta L, plugging in the Kerr-Newman black hole, and integrating it up on a space-like slice at t equals constant outside the horizon. So this is really remarkable because normally to compute these extremality shifts, it's somewhat painful. You have to actually solve for the perturbed Einstein equations and indeed solve the perturbed Einstein equations for your solution of fixed charge and angular momentum, and then examine those solutions and try and read off the shift in extremality parameter. So let me illustrate what that looks like for you here. Let's consider a quartic Riemann EFT. So R to the fourth operators, such as you might encounter in type 2 superstring theory. The Wilson coefficients C and C tilde are both positive, either by unitarity of graviton scattering or by causality. And I'm going to compute the corrections here in two different ways, explicitly using the perturbed metric or using the on-shell action formula. So here's the perturbed metric. Again, after you read off the deformed Einstein equations and sort of painfully solve them, you get the following. So it's the familiar Reissner-Nordstrom form plus corrections. And you examine that solution and you find that the perturbed extremality bound is positive. It's some order 1 number times this Wilson coefficient, C. But using the on-shell action formula, we can actually do much better. We can actually compute the shift in extremality for arbitrary charged and spinning black holes, which we can't do using the Einstein equations because it's not yet known how to solve those for deformed Kerr. So we can do that. So here it's an awfully complicated formula as a function of this spin parameter, but I can plot it for you. And indeed, it's positive for arbitrary spinning and charged black holes, and it agrees in the non-spinning limit with what we calculated explicitly from the metric. So that's nice. It's, again, black holes always kind of wanting to solve their own problems. So now, finally, let me argue why it is we believe that delta L is positive. That is, I connected the extremality shift to delta L. Now I want to argue that in healthy theories, delta L itself is positive as a consequence of unitarity. Right. So in particular, what I'm going to be thinking about are theories where the operators start at quartic order and higher in the fields. So I'm going to sidestep the issue of the infamous Riemann F² operator, though that's a really interesting question for future work. I also won't be talking about the issue of the T-channel singularity. If you're interested in that, please ask me after the talk if there's time, or in Slack. But basically, I'll be positing a weakly coupled UV completion so that we can sort of separate what's going on in the S squared over T part of the amplitude from the part of the amplitude that we care about that's generated by stuff far below the Planck scale. And so we can take T close to forward, but not exactly forward, and require that the UV scale is sufficiently far below the Planck scale that the non-T-channel singular terms actually win. Okay, so in a simple single-field EFT, whose poster child is the d phi of the fourth term, famously, this coefficient is positive as a consequence of classic dispersion relation arguments found in this paper. But we want to be much, much more general. We want to consider, ultimately, a general multi-photon theory for a multi-charged black hole. So as a warm-up to that, let's consider a general theory of multiple massless scalars with a shift symmetry. So here, it's like a d phi of the 4 operator, but each of the scalars is decorated with a flavor index, ijkl. And we have some tensors worth of Wilson coefficients, cijkl. And what I'll do is compute arbitrary phi-phi scattering, where here I, j, k, and l can be totally arbitrary choices of flavor. So I'm not choosing some particular elastic superposition, but instead letting the flavors be completely chosen arbitrarily. So in the forward limit, so that is the kinematic forward limit, but not necessarily the flavor forward limit, the amplitude goes like S squared at low energies. And so extracting this derivative, I can define this object mijkl, which is this particular combination of Wilson coefficients. So now just running through the standard analyticity and locality story, I do a contour integral around the origin, deform it to this new kind of double Pac-Man looking contour in blue, and I can write this big M as a sum over the discontinuities of the amplitude plus the crossed amplitude, integrated over the positive real s-axis. So now at this point, you might be expecting me to invoke the optical theorem, but instead I want to do something more powerful, which is apply the generalized optical theorem, by which I mean, let me write down these sort of half amplitudes for phi I, phi j goes to x, where x is an arbitrary intermediate UV state. And I can write these amplitudes in terms of two real matrices, MR and MI. So the contour integral tells me that these big M's are particular quadratic outer products of these unknown little m matrices that comprise the UV data of the theory. So let me write that more formally like this. And so these MIs are arbitrary, unknown, real n by n matrices that aren't in general symmetric or have any nice properties other than being real. So working through the symmetries of the tensor of Wilson coefficients, we arrive at this beautiful result, that cijkl can be written as the outer product of the symmetric part of the little m's plus the outer product of the antisymmetric part. And the former corresponds to the exchange of even spin states in the ultraviolet, and the latter corresponds to the exchange of odd spin states. Now, let me begin to tie this back to black holes. The two-derivative theory, the original theory, has an ON symmetry. And if I'm on a background that has a sort of no-hair theorem, so if I'm on a background transforming simply under this symmetry, like a generalization of the GHS black hole, where I replace the dilaton with some multiplicative dilitons, then d phi should look like some overall flavor vector times a 4 vector. So it should look like this outer product. And in that case, by virtue of this relation shown in gold that we derived using unitarity, we get that the action can be written as a sum of perfect squares. So now let's do that same thing, but for black holes. So I write down the arbitrary f to the 4th operators, and so I have two different types of Wilson coefficient tensors. And now I'm going to scatter photons of arbitrary flavor, but with real linear polarizations. And depending on whether I choose to scatter parallel or perpendicular polarizations as my incoming states, either Cijkl or C tilde ijkl are turned on, respectively. So I can again define these half amplitudes, these little m or little m tildes, and I effectively have two copies of the scalar case. So I can rewrite these Wilson coefficients by virtue of unitarity in terms of these outer products of m's. So now what I'm going to do I'm going to plug in the electromagnetic background for an arbitrary multi-charged ionic black hole. Because remember, to evaluate the shift in extremality, we have to look at what is delta L evaluated on shell on the black hole solution. So I plug this in, so I have an arbitrary vector of electric charges and another arbitrary vector of magnetic charges. And you find that delta L can indeed be rearranged in terms of a sum of perfect squares. And this follows, again, from unitarity and causality. So we get that the shift in this charge to mass ratio parameter is positive for arbitrary multi-charge dionic black holes. So this is a version of the weak gravity conjecture generalized to multi-charge theory. So the final thing I want to mention is this even works for Einstein-Maxwell-Dilaton theory, somewhat surprisingly. So here's the theory of Einstein-Maxwell-Dilaton. We have some dilaton coupling lambda, and I can write down the leading four derivative operators. And you can solve the perturbed Einstein-Maxwell-Dilaton equations of motion and find a new extremality condition that depends on the Wilson coefficients, A, B, C, and on this dilaton coupling lambda. And amazingly, we find that the extremality action relation continues to hold. That is, this shift here still goes like the on-shell action delta L evaluated on the background solution of the GHS black hole. And this is really surprising because the extremal GHS black hole is very different than extremal Reissner-Nordström. It's singular at the horizon, it has zero area in Einstein frame, black hole thermodynamics works differently, and so we're not really sure why this is still working. We have some speculation that it might be connected to the ADS2 times S2 solution in Einstein-Maxwell-Dilaton theory that I found earlier this year with Achilleus Porphyriadis, but this would be an interesting additional direction to look. So it looks like I'm just about out of time. So just to wrap up, again, we investigated the behavior of quantum or UV corrections to black hole extremality in two regimes, the asymptotic IR for exponentially large black holes and the threshold regime where the corrections are dominated by UV states. And the general conclusion in both regimes is that the black holes themselves can supply the weak gravity conjecture states, and this fact is enforced by unitarity and causality. There are a lot of open questions, some of which I've mentioned, are the two exceptional theories we found with huge numbers of massless fermions and non-minimal Planck scale couplings. Are those in the swampland? What can unitarity and causality tell us about RF squared operators? Can we apply any of the results we found to other swampland conjectures, like the distance conjecture or other versions of the WGC? And more speculatively, the extremality action relation suggests that the on-shell action is a really useful observable. Other interesting applications of the on-shell action that are worth looking at. But just to remind you of this picture of the Q over M curve, there's a lot of different physics encompassed in the different regimes of this curve. We know it's positive down here in all the different string theory examples that have been looked at. We know it's positive here by virtue of unitarity and causality. And finally, we know it's positive in the asymptotic IR by virtue of log running. So it's really cool that all sorts of different physics spanning from the deepest IR to the deepest UV are all kind of trying to tell us the same thing, which is that black holes like to be able to decay into other black holes. And this goes to the broader point of the WGC and the swampland program more broadly were originally thought of as sort of quantum gravity bounds that kind of couldn't be really touched from quantum field theory reasoning, from low energy IR first reasoning. And what we've been finding recently is that actually the WGC can be understood both from a top-down and bottom-up point of view. And that's really exciting to be able to kind of unite those two points of view. So with that, I'll take any extra questions you have, and thanks very much.
Okay, so thanks a lot, Grant, for that very clear presentation. Are there any questions for Grant? Now I'll keep an eye here on the audience as well, if I can do that. Yeah.
I have a question.
Yep.
I think it's likely that if one ran the kind of dispersive gravitational EFT bounds that I talked about this morning, in the case of f to the fourth, it would be allowed to be a little bit negative.
Right.
So, you had a dispersive argument that it was positive, but I think that makes it clear that your dispersive argument for positivity was relying on this additional assumption that you put in.
That's right. That there, indeed. So when I think this comes down to how I drop the T-channel singularity, right? Because I'm invoking a weak coupling assumption, which is that I'm sort of not exactly forward, but near forward. Specifically, that I can write T as alpha m star squared, where alpha is some number much less than 1. And in that case, I get that the s squared over t part of the amplitude is small compared to s squared over m star to the fourth, provided alpha is much bigger than m star squared over m Planck squared. So as long as m star squared over m Planck squared is really small, I can sort of neglect the 1 over t part of the amplitude. But indeed, that's an argument that leaves open the door for a lot of subtlety if you kind of want to relax some of those assumptions.
Right. I mean, I think that the dispersive bounds would definitely allow negativity for the coefficient. So one question is whether you think there should be some additional consistency conditions that go beyond dispersive bounds on 4-point amplitudes, and if so, what do you think would be the observables to look at?
Right. I mean, so indeed, I know that f to the fourth can go negative in some theories because I exhibited one at the beginning of this talk, right? The theories with large numbers of
right, but
massless states.
This is about negativity in the threshold region.
Right. So I suspect that. Let me see. I do think that you would have a hard time generating negative f to the fourth without also generating RF squared terms, for example. So it seems like anytime your theory is starting at purely at quartic order and higher, then and again provided that you're in a weakly coupled UV completion, that it would be sort of hard to run into some of these counterexamples. At least I don't know of any examples that don't also run afoul of one of those assumptions.
Can I make a quick comment? When there's no weak coupling, so there's only one scale, M Planck, then there's no real invariant distinction. There's no real invariant notion of higher dimension operator that comes from the UV or comes from the threshold, precisely because it's dominated by the massless states in the low energy theory. So that's a sense in which the two parts of Grant's talks are related to each other. If you do have a weakly coupled UV theory, then there are just the flat out clean positivity bounds. If you don't have a weakly coupled UV theory, then the notion of higher dimension operator is ill-defined, and you should compute the logarithmic corrections which dominate. And well, that's what he talked about. So now in high enough dimensions, the distinction, there is a little bit of distinction just by dimensional analysis, because just gravitational loops will not generate all higher dimension operators just because of units. But in 4 dimensions, they do. So which is what we're talking about here. In 4 dimensions, if there's no other scales other than M Planck, then you already generate f to the fourth just from log running in the low energy theory. And so either there's a weak coupling, so the threshold corrections dominate, or there's not, but the logs dominate. And almost always, except for these weird counterexamples that Grant talked about, the signs worked out right.
Right.
Maybe take a question from the internet, from Zoom.
Yeah, it looks like Brando has a question, perhaps.
Yeah, hi Grant, can you hear me?
Yeah, hi Brando.
Hi. So I have a question about the case when, do you have examples where the one loop beta function vanish and you're forced to go to maybe perhaps by supersymmetry, and
Well, sure.
and then wait a second, and then you have to go to two loops, include the FETs of FF Riemann, for example, and see how things evolve.
I mean,
the case.
So that's an interesting question. I mean, so let me see. The one loop beta function vanishes in n equals 2 supergravity. I mean, for supergravity reasons. So let me see.
Perhaps in that case, FF Riemann vanishes as well.
But yeah, FF Riemann
okay.
has to vanish again by Susie.
Okay.
So
Yeah,
I don't know of a non-Susie case.
Obviously.
Yeah. I don't know of a non-Susie case where this beta function vanishes.
Although, Grant, I suppose one could a la Bank-Zaks. One could imagine tuning in those examples where we get a minus sign. We could imagine tuning the coefficient to be very small, and then we could go from there. But all the examples where it's naturally zero are where it's zero for BPS reasons and it's zero non-perturbative.
Right.
Yeah. Okay. Thank you very much.
Okay, in view of the time, I suggest we move on, but I remind people that there is a Slack channel for the conference where you can ask further questions and get answers in the next few days. So let's thank Grant again for that very nice talk.
Thanks.
Okay, so our next speaker is Nima Akani Hamid. Now, Nima, are you able to share